This is our welcome to calculus, and to try and get you up to speed a little bit with what to expect, we're going to look at the number of cases of COVID for Michigan between March 1st and April 20th, 2022. Now, in that data, you could look at and try and figure out, well, how are things changing? And to do that, maybe you'll pick a couple of different cases and figure out, well, what's the slope of the line between those two cases? And the slope of the line tells you the average rate of change. Now, the average rate of change, okay, that's great, but the state epidemiologist is not going to be interested in how things are changing on average. They're going to want to know things, not a 3-week average of about 52 cases a day. You want to know, well, what's happening to it right now? How is it changing? So to investigate that a little bit more, we fit this model to our data. We're going to look at that. We're going to look at the rate of change within this model. But like I said, a 3-week rate of change doesn't do us too much good. So let's get rid of the actual data here and get rid of the visualize the slope. And let's take a look at things. Let's see, is this one? No, not this one. Here we go. Let's take a look at this line here. This is our line, and the slope of this line tells us the average rate of change, but it's for 3 weeks' time. We will live in a 24/7 world. We want to know how things are changing like right now. So looking at an average over 3 weeks doesn't do us too much good. So you could say, well, what if we looked at a shorter time period? Made that a little bit shorter. Okay, well that's better. But now maybe you're looking at 2 weeks as opposed to 3 weeks. So still not quite fast enough. And this is still stuff you can do in college algebra. Calculate the slope of line. Well, let's get a little closer, or a little closer. And pretty soon, these 2 points almost coalesce. And instead of getting an average rate of change, you're getting what's called the instantaneous rate of change. Now, there's a couple things here that I want to foreshadow for you for this course. So one of them is this process right here, where we're changing this interval and we're letting that interval of time get shorter and shorter and shorter. That's a limit process. That's the first thing we're going to do in this course. We're going to do this today right after this section, is we're going to find, well, what's the limit? What happens when you let things go and get arbitrarily close to something, or let them get arbitrarily large? What happens? Now, the second part of this course talks about what this is right now, and that's going to be a derivative. The derivative function is derived from the function itself, and it tells you, amongst other things, the instantaneous rate of change. How is it changing right now? So not how is the caseload of COVID changing over 3 weeks' time, how is it changing right now? And that instantaneous rate of change is going to have a lot of applications. We're going to spend some time working with those applications and understanding them. And there's going to be a lot of work that we're going to spend on understanding the derivative function. So that's a good 2/3 of this course right there. Now let's get rid of this for a moment. And Ethan mentioned something about the area underneath the curve. And that's going to be the next thing that we're going to work on in this course. It's going to be kind of towards the end of this course, and the last thing we're going to end up with this in this course. So how could you find the area underneath this curve, say, for the first 48 days after March 1st? Well, it doesn't really fit a nice geometric pattern. It's not a triangle or a rectangle or stuff like that. So one thing you could do would be to estimate this area by using some rectangles. And what do you think? Is that a good estimate of the area under this curve if I just use a rectangle like that? Probably not so good. So what could we do? Well, we could add more rectangles. Add 2. Still not so good. 3, 4, 5. But as we add more rectangles, how's that estimate looking? Is the area underneath these rectangles looking a little bit better? Yeah. And this is what we're going to do to finish up the course. Is we're going to try and find the area underneath these curves. But notice what's happening right here. You're still looking at another limit. You're taking the limit as the number of rectangles tends towards infinity. Now, I've got this set up with a maximum of 100, but I mean, after a while, you're getting a pretty good estimate of the area underneath this curve. And an amazing, theorem that ties the first part of this course together and the second part of this course together. The process that we did earlier to try and find the slope of the tangent line at this point, or the instantaneous rate of change, when you do the opposite of that process, that's going to give you the area underneath this curve. So it binds these two things together. It's the fundamental theorem of calculus. It's just amazing how well it works out. And if you actually, take a look at this, right now we've got an estimate of about 50,010. The actual exact area would be, 50,317. So you actually get a really good estimate with just a small number of triangles, or rectangles, I should say. If you total up the real data, we're within less than 1% with this estimate. So it's really good. But overall, that's where we're headed in this course, is doing these things. We're going to start out by working with limits. Limits are going to turn into derivatives. Derivatives are going to have some applications. And then from there, we're going to try and find the area underneath this curve and apply that to a couple things. The rest of the applications are going to come in Calc 2. So that's where we're headed. Comments or thoughts on that? Doing okay there? All right. Let's put this one in the books.